Obtain the mesh file and the full training movie via this link. The problem simulates the flow of fresh air through the air conditioning system inside a clean room considering the coronavirus. We place the patient on a bed in a room with a high temperature on his body and constantly spreads the coronavirus particles by breathing through his mouth into the room's interior. In fact, the goal is to use an air conditioning system and keep the fresh air flowing continuously inside the room to remove contaminants from the patient's mouth through the outlet vents. And the room environment should be purified in terms of pollution, and a balanced and pleasant temperature should be provided for the thermal comfort of the patient inside the room. There are two main issues in the CFD simulation. The first issue is that the flow of the coronavirus in the respiratory must be defined through the patient's mouth, for which we use a discrete phase model or DPM. Because in this model we track the particles of the coronavirus, we apply this type of view or Lagrangian view in examining the behavior of particles. In the present model, the fresh airflow from the upper vents of the room has a velocity and a defined temperature. The patient's body surface temperature is equal to a constant value, and the virus particles are injected from the patient's mouth in a specified rate and temperature, and also defined diameters. The present model is three-dimensional and is drawn using design modeler software. The model consists of a cubic room, so that a hospital bed and a patient are designed on it. Also, 6 circular holes are considered as fresh air inlet flow, and 5 rectangular holes are considered as flow outlet sections in the side walls of the room. The left figures show a view of the geometry, and also the meshing is done using ANSYS meshing software. The mesh type is unstructured. Cells are smaller in the areas adjacent to the internal boundaries and have higher accuracy. The right figure also shows a view of the mesh. Thermal comfort is a state of mind separate from the equations of heat transfer and mass and energy balance. But it comes from the concept of thermal comfort, which is one of the variables that affect the mass and heat transfer in the energy balance model. The most common perspective used to describe thermal comfort for estimating and designing buildings has linked the results of psychological experiments and variables to thermal analysis. In fact, a lot of experiments have been done on humans at universities, and these people have different clothes or are doing different things in different situations. Also, the environment in which the experiments are performed has different air temperatures, different surface temperatures, different humidity levels, different airflow velocities, and different airflow patterns. Then the level of comfort of human beings was measured in different states, and the response of their average thermal sensation was examined. As a result, the predicted mean vote, or PMV, for thermal measurement was obtained in the form of the ASHRAE thermal scale. The values for this criterion vary between -3 and +3, and according to this table, the different states of heat sensation range from very cold to very hot. Relationships for PMV are divided as a function of 6 variables, including air temperature, average radiant temperature, air velocity, air humidity, wear resistance of clothing, and type of physical activity. Finally, the PMV relationship is obtained like this formulation as a function of the thermal charge, or L, on the body, which is the difference between the rate of metabolic heat production, or M, and the calculated heat loss from the body to real environment condition is defined. There is also a fundamental relationship between the predicted percentage dissatisfied, or PPD, and a thermal environment as a function of PMV. As the PMV goes to +3 or very hot and -3 or very cold, the PPD increases, meaning dissatisfaction increases. While moving to 0, the PPD decreases and dissatisfaction also decreases. It is injected into the inner space of the hospital room from the patient's mouth. The type of injection process is surface, and the type of coronavirus particle is inert. All the walls in this CFD simulation, including bed, mouth, human body, and surrounding walls, all of them are a stationary wall, and the shear condition is no slip. Also, you can insert a number in the autosave every iteration section if you are going to autosave your time steps and extract the data along the simulation. This is the top view of the three-dimensional pass lines that the flow enter from the 6 different inlets in the ceiling and exits from the 5 different outlet section in the side walls. As we can see in this three-dimensional particle tracking, the particles and flow exit from the patient's mouth and enter the clean room environment, and then exits from the 3 closest inlets. By extracting this result, we can see that the ventilation performance is acceptable, and also we know that in which direction the particles are going. Here is a summary of the steps for defining the problem and its solution in these tables. Obtain the mesh file and the full training movie via this link. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com. Hope you enjoy.